A linear regression is the hello world of machine learning, the one we all start with. It tries to model the relationship between variables, in this case, these data points, using a straight line. We can start with an initial guess for the line, but it usually won't fit the data perfectly. By adjusting the slope and intercept, we find the line that minimizes the total error, the differences between the predicted and actual values. These small vertical lines show those differences, known as residuals. The line that minimizes all of them is our best fit line, and that's what linear regression finds. This is the general equation of multiple linear regression. Multiple meaning in more than one dimension of x. Now we are going to derive the explicit formula for multiple linear regression. We will start with a single observation linear model. Here beta naught through beta p are the parameters we want to learn, and epsilon I is the residual, the part of yi not explained by the linear model. Beta naught is also called the bias or the intercept, while the other beta values are called the coefficients or the weights. To work with an entire data set of n observations, we stack these equations into its matrix form. We write y equals x tilde beta plus epsilon, where x tilde is the design matrix that includes a column of ones for the intercept. Y hat is the predicted value from linear regression, which equals xw plus b, where x is almost exactly the same matrix as x tilde, but without the leading column of ones, so we are separating the weights from the y-intercepts, but both representations are the same. From here on out, I'm going to call the x tilde matrix x. These are all the vectors slash matrices, except y hat. Our goal, as always, is to minimize the error. The most common cost function in regression is the mean squared error, also called the sum of squared residuals. We need to find the coefficient vector beta that minimizes the sum of squared residuals. That equation can be rewritten in matrix form as follows. After some expansion and simplification, we get the following equation. To find its minimum, we will take its partial derivative with respect to beta and set it to 0. At the end, we get the normal equations. Note, this is linear algebra, and we can't exactly cancel out the x transpose matrices from both sides. Instead, we need to multiply both sides with the inverse of x transpose times x. If that matrix is singular, then infinitely many solutions for beta exist. This is the least squares estimator. Geometrically, it projects the observed vector y onto the column space of x. A couple of quick practical notes. If x transpose times x is ill-conditioned or singular, use a pseudo-inverse or regularization, like ridge regression. Numerically, computing the inverse of x transpose times x transpose can be unstable for large or collinear feature sets. QR decomposition, or SVD, are more robust. So that's the closed-form derivation of linear regression. Build the design matrix, minimize the sum of squared residuals, take derivatives, solve the normal equations, and you get the desired formula. Now let's take a look at regularization. Here's our data set. Noisy observations of a simple relationship. Now we will force a polynomial regression model to perfectly interpolate every single point. Then, as you can see, it does fit perfectly, so zero bias, but it has extremely high variance and is overall a terrible model. This is overfitting. The model is fitting noise, not the underlying pattern, and will perform badly on new data. Although this is just an example and isn't the type of overfitting we are focusing on here, Instead, what we are going to do is slightly reduce the weights in the linear regression model, as empirically we know that the average correlation between random features in a dataset is 0. So when there isn't a lot of data, it is safe to assume that the true coefficients are going to be slightly closer to 0 than what the model predicts on average. By adding a penalty term, big coefficients get fined. This idea applies to many models, including linear regression, and is called regularization. The penalty term also controls complexity. First, ridge L2 regression. The penalty here is proportional to the square of the coefficients. Geometrically, we draw contours of the loss, those nested ellipses, and overlay an L2 constraint, a circle. The ordinary least squares solution sits somewhere off-center. When we enforce the circle constraint, the optimal solution is where a contour first touches that circle tangentially. You can see the solution moves inwards. Ridge shrinks coefficients towards 0, but doesn't set them exactly to 0, unless they are already exactly 0. It's great for stabilizing estimates when features are correlated or noisy. Now lasso regression, which uses an L1 penalty, proportional to the absolute values of coefficients. Its constraint region is a rotated square. The geometry matters because the square has sharp, protruding corners aligned with the axes. The first contour to touch it sometimes lands on one of the corners. That means lasso can set coefficients exactly to 0, performing implicit feature selection. So lasso both shrinks coefficients and can sparsify the model. Very useful when you suspect many features are irrelevant. Elastic net blends the two, an L1 part for sparsity and an L2 part for stability. The constraint region becomes a rounded square, a hybrid shape, which can zero out some coefficients while still stabilizing correlated features. Practitioners tune the mixing parameter to favor more L1 or more L2 depending on the problem. This is determined by alpha, a number between 0 and 1. In the current shape, alpha is set to 1/2. Quick recap. Ridge, L2, shrinks coefficients, good for multi-collinearity, doesn't set coefficients to 0. Whereas lasso, L1, encourages sparsity and performs feature selection by zeroing coefficients. Elastic net combines L1 and L2 to get sparsity plus stability, helpful when features are correlated. A few practical tips. Always scale your features before regularizing, and pick the penalty strength, the lambda, by cross-validation. That's how you balance bias and variance in practice. For large data sets, computing the exact analytical solution can be expensive, so we use gradient descent. On the left are our data points and the ideal regression line. On the right is the loss surface, showing how error changes with slope and intercept. The green dot marks the global minimum. That's the best fit model. We start from a poor initial guess. Now let's watch gradient descent in action. This demo uses Atom, an adaptive optimizer that adjusts step sizes as it learns. It's faster and smoother than plain gradient descent. I'll cover Atom and other optimizers in a future video. The learning rate controls step size. Too high and you overshoot. Too low and convergence drags. But overall, this is the idea. Follow the downhill direction of the gradient until the error can't get any smaller. Here we'll see why polynomial regression is really just ordinary linear regression in disguise. The trick is how we build the features. First, this is our data set. Noisy samples coming from a smooth nonlinear function. Pick one x value from the data set. Instead of feeding x directly into the model, we map it to a feature vector. Phi of x equals the vector 1, x, x squared, x cubed, and so on, till the degree of the polynomial. That vector contains simple, nonlinear functions of x, powers of x. But notice, Once we've made those features, the model is linear in the coefficients. A Vandermonde matrix is built by taking each input value and expanding it into its feature vector. For polynomial regression, each row becomes 1, x, x squared, x cubed, and so on. And stacking these rows gives us the Vandermonde matrix. These columns, the powers of x, are what our linear solver uses to find the best coefficients. So although the model looks nonlinear in x, the prediction is equal to phi of x transpose times beta, a dot product between the feature vector and a coefficient vector beta. We solve for beta using the same least squares normal equations you already know. Higher degree polynomials clearly have lower bias, but with a higher degree, you can sometimes start fitting noise, increasing variance. That's the risk of too much flexibility. The key takeaway? The only nonlinearity is in phi of x. Once you build those features, you're back to a linear model in beta. That's why we can reuse all linear regression tools, closed-form solvers, regularization, and so on.